Hi, this is the sixth lesson in electricity. In this lesson, I'm going to discuss about the use of voltmeter in a circuit. Say mainly, normally we say that the internal resistance of a voltmeter should be very large, is it? But what will happen if the internal resistance of a voltmeter is smaller? So this large, small. Say for example, we say internal resistance of a voltmeter should be very large to have accurate reading. What do you mean by that? What's the meaning of internal resistance of a voltmeter should be very large? Okay, so I'm going to discuss about that one. So we'll consider a simple circuit to understand the reason why should a voltmeter have larger internal resistance. Okay, so here a simple circuit where two components. I told earlier we don't consider the function of the component, we consider only the resistance of the component in electricity. So the first component, its internal resistance is R1, and the second component, its internal resistance is R2. Okay, so according to potential divider method, the voltage across the first component is, the voltage will be divided according to the ratio of the resistance of the component. So that will be EMF times R1 over R1 plus R2, right? So I'm going to measure the voltage across the first component, which has resistance R1. I'm going to measure the voltage across it by using a voltmeter. So what should I do? I should connect the voltmeter across that component. So remember that voltmeter always reads the voltage applied across the two terminals. Okay, the voltmeter reads always the voltage applied across its two terminals. So that means I can say voltmeter reads, if I connect a voltmeter across these 2 points, it will read the voltage across those 2 points. Voltmeter has internal resistance due to its components inside. It will have internal resistance. So I can say like this: voltmeter reads the voltage applied across 2 points. So those 2 points should be across the components. At the same time, the voltmeter reading will be equal to voltage across its internal resistance. Okay, so here voltmeter is connected across R1 because I want to measure the voltage across that component. So the voltmeter reading will be equal to voltage across the resistance R1. R1 is the resistance of the first component. So voltmeter reading will be equal to voltage across R1, that will be equal to same as the voltage across the internal resistance of the voltmeter. So I can, here also I always tells that when you are in electricity, we don't consider the function of the components, we consider the resistance of the components. When we are calculating current or when we are calculating voltage across the component, we don't consider the function, whether it's a bulb or whether it's an electric motor or whether it's a heater, whatever it is, we consider their resistance. So here also I can think about the internal resistance of the voltmeter. I can imagine a voltmeter like a component that has resistance RV, but it has a display to show the voltage. I can simply like that. I can think like that. Okay. So here the voltmeter reading will be equal to same as voltage across R1. That will be same as the voltage across RV. Okay. So here, since the voltmeter is connected across R1, it looks like voltmeter is in parallel connection with R1 because that satisfies the condition for parallel connection, is it? So a current I comes, it splits at this junction I1 IV. Again they rejoin, here the current is coming here I1. So at this junction again I1 and IV rejoin and forms I. So I can say voltmeter is connected in parallel to the component which has resistance R1. But actually we should say voltmeter is connected across the component, right? So you know that when components are connected in parallel, the voltage across the components, those are in parallel, will be the same. That will be same as the voltage across the equivalent resistance of those components. So I can think about the equivalent resistance of RV and R1, and I can call it as R0. So I'm going to draw the circuit again, so that will be helpful to find the reading of the voltmeter. So the voltmeter reading will be same as the voltage across R0, where R0 is the equivalent resistance of RV and R1. So here the voltmeter reading will be equal to voltage across R0. What is R0? R0 is the equivalent resistance of R1 and RV, right? So I can say 1 over R naught equal to 1 over R1 plus 1 over RV. Okay, so now the voltmeter reading is same as the voltage across R naught. So voltmeter reading is equal to will be equal to voltage across R naught, means I can again use potential divider method for this circuit to find the voltage across R naught, that will be equal to EMF times R naught over R naught plus R2. See, now actual reading is actual voltage across R1. That's the aim of this experiment. I want to measure the voltage across R1. So the actual reading of R1 is voltage across R1 is EMF times R1 over R1 plus R2. But here the reading is going to be EMF. So same as this one, EMF. R2 same, but the only difference is instead of R1, it has become R0. It has become R0. Because of the internal resistance of the voltmeter, it's going to be different now. Okay, now look at here. If I want to get exactly the actual value as the reading is going to be different. You can see that the reading is EMF times R0 over R0 plus R2, but actual voltage is EMF times R1 over R1 plus R2. So they are not same. You know that they are not same because EMF is the same, R2 is the same. Here R1 in the numerator, here R1 in the denominator, but here R0 are there. So we know that 100% sure the reading is not same as this one. You see. So what is going to happen now? How can I get actual value as a reading? The only thing is the reading R naught is 1 over R1 plus 1 over RV. So if R naught is equal to R1, then the reading will be exactly same as the actual value, actual voltage across the R1. So if R naught wants to be equal to R1, what's the condition? 1 over RV should be small, that is almost equal to 0. If 1 over RV is almost equal to 0, then 1 over R naught will be equal to 1 over R1. Then R naught will be equal to R1. So R naught will become equal to R1 means the reading will be equal to actual value. You understand? So that's the reason we say normally the internal resistance of the voltmeter should be very large. But I tell you a reason. What we say internal resistance of the voltmeter is very large is not actually 100% correct. We should say internal resistance of the voltmeter should be very large compared to R1. Compared to R1. Right? I'll do it through a calculation and explain it later. But here I can say the RV should be very large means almost equal to 0. When this becomes almost equal to 0, 1 over R naught will be equal to 1 over R1. So R naught will be equal to R1. Then the reading will be equal to reading will become equal to the actual value R1 EMF times R1 over R2. So that's the reason we say the internal resistance should be very large. So I can say when RV is very large, then 1 over RV almost equal to 0, then 1 over R naught equal to 1 over R1 plus 0. So then that will become R naught equal to almost equal to R1. So the reading will become equal to, what will be the reading then? Then reading will be equal to EMF times, instead of R naught I can put approximately R1 over R1 plus R2. Then it will be more closer to the actual voltage across R1. Okay, so if we want to get accurate reading as the actual value, the internal resistance of the voltmeter should be very large. Okay, so if the internal resistance of a voltmeter is not very large, what will happen to the reading? Okay, so look at here. This is the actual voltage across R1. So this I can write EMF times, divide numerator and denominator by R1. So that will be into 1 over 1 plus R2 over R1. So I'm just taking this format to explain what will happen to the reading if the internal resistance is not very large. right? So I divided numerator and denominator by R1. So you will get this one. This is the actual voltage across it, right? So when components are connected, when voltmeter is connected in parallel across this one, across the across the R1, the volt, okay, the equivalent resistance is R naught. So here the voltmeter reading is going to be, we know that 1 over R naught equal 1 over R1 plus 1 over R1, RV. So reading will be equal to EMF times R naught over R naught plus R2. Here also divide numerator and denominator by R naught. You will get EMF times 1 over 1 plus R2 over R naught. Okay, now I can say what will happen to the reading if the internal resistance is not, internal resistance of a voltmeter is not very large. Okay, you can see that always the equivalent resistance is smaller than R1. When components are connected in parallel, we know that the equivalent resistance will become smaller than or lower than the resistance of the component. So R naught is lower than R1 as well as R naught is lower than RV. So here I can say R naught is lower than R1. R naught is lower than R1. So R2 over R naught, when you compare R2 over R naught and R2 over R1, R2 over R1 and R2 R naught, when you compare, R naught is lower than R1, so R2 over R1 is greater than R2 over R1. Little bit mathematics I am using, algebra, simple algebra. So R naught 2 over R naught is greater than R2 over R1 because R naught smaller than R1. Okay, then what will happen to the reading here? 1 over 1 plus this value is larger than this value, means here the denominator is larger than this denominator. So the reading will be lower than the actual voltage. Understand? So what will happen? The reading of the voltmeter, if the internal resistance of the voltmeter is not very large, what will happen? The reading of the voltmeter will become lower than the actual voltage across the component. Okay, to understand the effect of internal resistance of a voltmeter, we'll do one or two questions related to voltmeters, how to calculate the reading of a voltmeter. Okay, so this is a circuit. So in this circuit, two components with resistance 5 kilo ohm, 10 kilo ohm are connected in series with a power supply which has EMF of 16 volt, right? So we are going to measure the voltage across 10 kilo ohm. So I'm going to introduce two different voltmeters. First, I'm going to connect a voltmeter across 10 kilo ohm. The internal resistance of the voltmeter is 30 kilo ohms. And what could be the reading of it? Then I am going to connect a voltmeter across the same 10 kilo ohm resistor, which has internal resistance. The voltmeter internal resistance is 50 mega ohm. You will see when the voltmeter has 50 mega ohm, its reading will be more closer to the actual voltage across 10 kilo ohm. So we'll first find the actual voltage across 10 kilo ohm. So I can call this V1, this is V2. The reading, the actual voltage across 10 kilo ohm resistor I can find by using potential divider method. So that will be 16 into 10 kilo ohms. So I'm not going to convert to ohms because both are in kilo ohms. So I'll keep it in kilo ohms. So they'll get cancelled. 10 over 5 plus 10. So the voltage across that one will be, you will get 10.67 volt. 10.67 volt. So that's the actual voltage across 10 kilo ohm resistor. So I want to measure that, right? So you know that when we are using an instrument to measure a particular physical quantity, the instrument should not alter the actual value. Say for example, that is true even for thermometer. Say for example, there's a liquid in a container. So you are going to measure the temperature of that liquid right? When you keep a thermometer, liquid in glass thermometer, something like mercury thermometer, you know thermometer absorb little bit of energy, little bit of heat for to expand the mercury. So actually it's absorbing some heat, means the temperature of the liquid will go down, right? But it should not happen drastically. The temperature of the liquid should not drop a lot, because if the temperature of the liquid drops a lot because the mercury is absorbing the heat, then the reading will go wrong, right? So that is true for any measuring instruments in physics, not only physics, in anywhere, even in chemistry or wherever. When you are using an instrument and when that instrument is reading, it should not read, it should not alter the actual value of that quantity. Okay, so we are going to check whether the voltmeter, when I connect across 10 kilo ohm, which has internal resistance of 30 kilo ohm, will it read the same value as the reading? We'll see that. Okay, so a voltmeter that has the internal resistance 30 kilo ohm is connected across 10 kilo ohm. So I told that voltmeter reading will be same as voltage across 10 kilo ohm. That will be equal to voltage across the internal resistance of the voltmeter, which is 30 kilo ohm. The voltage across 30 kilo ohm is same as the reading, and that will be same as the voltage across the equivalent resistance of 10 kilo ohm and 30 kilo ohm. So we will find the equivalent resistance of 10 kilo ohm and 30 kilo ohm. So 1 over R naught equal to 1 over 10. I'll keep it in kilo ohm, 1 over 30. So R naught will be equal to 7.5 kilo ohms. Okay, so now I can imagine this 7.5 kilo ohm is connected in series with 5 kilo ohm. I can replace these two resistance by this one. So that will be in series with this one. So if I connect it like this is 16 volt, 5 kilo ohm and 7.5 kilo ohm. So voltage across 7.5 kilo ohm is the reading of the voltmeter, because that is R naught. That is R naught, right? So I can say voltmeter reading is equal to voltmeter reading will be equal to, I should find the voltage across 7.5 kilo ohm. So I can use the potential divider method. 16 into 7.5 over 5 plus 7.5. So that will be equal to 9.60 volt. You can see that this will be the reading of the voltmeter. That is not equal to actual voltage across 10 kilo ohm. I want to measure the voltage across 10 kilo ohm. So actual voltage should be this one, but the voltmeter is reading 9.60 volt if its internal resistance is 30 kilo ohm. Remember that value, 9.60 volt. So it's much difference. Almost 1.07 volt is lower, is it? Okay, so now I'm going to connect another voltmeter. I'll replace this voltmeter by another voltmeter that has internal resistance of 50 mega ohm. 50 mega ohm means 5 into 10 to the power 7 ohms. We will see what will happen to that reading. Okay, so now I replace that voltmeter by another voltmeter which has internal resistance 50 mega ohm. That is 50,000 kilo ohms. Is it? 50 mega means 50 into 10 to the power 6 ohms. So if you convert to kilo ohm, 50 into 10 to the power 3 kilo ohms. That is 50,000 kilo ohms. Is it? 50 mega ohm means 50 into 10 to the power 6 ohms. If I want to convert this to kilo ohm, divide by 1000, you will get 50 into 10 to the power 3 kilo ohm. That is 50,000 kilo ohms. Okay, so now this voltmeter has internal resistance 50,000 kilo ohms. Okay, so what will be its reading? Earlier when we used voltmeter that has internal resistance 30 kilo ohm, that gave a reading of 9.60. Actually, it's much different from actual voltage. We will see what happened when the internal resistance of the voltmeter is much larger compared to earlier voltmeter. Right, so here also we need to find the equivalent resistance. You know, voltmeter reading is same as the voltage across the equivalent resistance of the RV and 10 kilo ohm. So 1 over R naught equal to 1 over 10 plus 1 over 50,000. I'll keep it in kilo ohms. So if you solve it, you will get R naught is equal to 9.998 kilo ohms. 9.998 kilo ohms. So, you know, very closer to 10 kilo ohm. So you can see that when the interface of the voltmeter is very large compared to this one, it's becoming closer, very closer to the actual voltage. Sorry, it becomes very closer to the resistance of the component, that is 10 kilo ohm, 9.998 kilo ohm. So now I can imagine this equivalent resistance is connected in series with 5 kilo ohm. So if I connect the same circuit like 16 volt, this is R1, 5 kilo ohm. This is equivalent resistance R naught, that is 10 kilo ohm, or 9.998. I can take it as 10 kilo ohm, that is R naught. So voltmeter reading will be equal to voltage across R naught. So now I can see voltmeter reading. Voltmeter reading will be equal to EMF, that is 16 into 10 over 5 plus 10, same as this one. It will be 10.67. So now you can see that the voltmeter reading becomes almost equal to, or mainly equal to, the actual value across the 10 kilo ohm. So you can see that when the interface of the voltmeter becomes very large compared to 10 kilo ohm, the voltmeter reading becomes almost or very closer, or it looks like equal, but actually 9.998. I replaced it by 10 kilo ohms. Even if you use 9.998 here, it will be very closer to actual voltage across the component of 10 kilo ohm resistor. Okay, so that shows that when the interface of the voltmeter is lower, the reading has much difference compared to the actual value. But when the interface becomes very large, the reading approaches or becomes very closer to the actual voltage across the component. Okay, now I'm going to use this 50 mega ohm resistor in another circuit. We are going to check whether this voltmeter, which has interresistance of 50 mega ohm, which is giving actual reading in this circuit, it's giving a correct reading in this circuit. Will it give correct reading in that new circuit? I'm going to check it. We'll see that. Okay, so we are considering another circuit where two components, those have resistance 60 mega ohm and 80 mega ohm, connected in series with 16 volt power supply. So here the actual voltage across the first component, which has internal resistance of 60 mega ohm, will be equal to 6.86 volt. I use potential divider method, so EMF times this resistance over total resistance. You know, voltage will be divided at the ratio of their resistance when they are connected in series. So I use that potential divider method here. So voltage, actual voltage across 60 mega ohm is 6.86 volt. Okay, in the previous circuit, we found that the voltmeter that has 50 mega ohm, looks very high resistance, gave a very accurate reading that is very closer to the actual voltage. So I am going to use that voltmeter which has internal resistance of 50 mega ohm to measure the voltage across this one. We will see what will happen to the reading. Okay, so that voltmeter is connected across 60 mega ohm resistor. That voltmeter gave very accurate reading in our previous circuit. We will see what happened to the reading now. Okay, so we know the voltmeter reading will be same as the voltage across the equivalent resistance of 60 mega ohm and 50 mega ohm. So 1 over R naught equal to 1 over 60 plus 1 over 50. I'll keep them in mega ohm. So R naught will be equal to 27.3 mega ohm. Right, so I should find the voltage across 27.3 mega ohms. So I can imagine the circuit. This is 16 volt. So I can imagine the circuit like this, 16 volt. This is R naught. That is 27.3 mega ohm, and this is 80 mega ohm. Okay, so the voltmeter reading will be equal to voltage across R naught. What will it be? We'll see that voltmeter reading. So if I use potential divider because they are in series, so 16 into 27.3 over 27.3 plus 80. So the voltmeter reading becomes 4.70 volt. See what happened now? Earlier, that voltmeter read in the previous circuit very accurate reading. The same voltmeter when I connect in this circuit, the reading is 4.70 voltage. That's the voltage across this one. 60 mega ohm is read by this voltmeter as 4.70 volt. But actual voltage across it is 6.86 volts. See, very big difference. Much larger difference between the reading and the actual voltage when I use a voltmeter that has larger resistance, 50 mega ohm. So what do you understand by the statement? To have actual reading, the internal resistance of the voltmeter should be very large is not 100% accurate. Actually, what should we say that to have actual reading, the internal resistance of the voltmeter should be much larger compared to the component, the resistance of the component across which we are measuring the voltage. Again, I'm saying to have actual reading, what's the condition? The internal resistance of the voltmeter must be very large compared to the resistance of the component across which we are measuring the voltage. Okay, so that's the reason. Say when you compare the voltage of the resistance across which we are measuring the voltage, the resistance is 60 mega ohm. Internal resistance of the voltmeter is 50 mega ohm. They are very comparable. They are comparable, not much difference. Like they are almost same in terms of resistance. But earlier circuit, this gave an actual reading because compared to that resistance, earlier we used that resistance was 10 kilo ohms. Compared to 10 kilo ohms, 50 mega ohm, earlier circuit, compared to 10 kilo ohm resistor, 50 mega ohms is much larger, much larger. So it gave a reading, correct reading. But here, it's not like that. That's a reading. It's giving a wrong reading. Actually, a big difference compared to actual reading, actual voltage and the reading. Okay, so the simple statement, internal resistance of the voltmeter should be very large is not enough. We should say the internal resistance of the voltmeter should be very large compared to resistance of the component across which we are measuring the voltage. That should be the actual statement. I hope you understood through this example the meaning of the reading of a voltmeter and what do we mean by high resistance of a voltmeter. Again, I am telling it, internal resistance of the voltmeter should be very large compared to resistance of the component across which we are measuring the voltage. Okay, right, bye.